Hello, welcome to Medline. In this session, I'm going to discuss about digital radiography. So I'll start presenting now. So today's topic is digital radiography. So we know that radiography is an art and science of recording images produced by X-rays on an X-ray film. Till the past decade, the conventional film screen system was the most widely used and accepted method of recording images, wherein the film acts as an image receptor, display medium, and a source of permanent record. Though these films are relatively inexpensive and provide high image quality, they have many limitations. So we have advanced into digital radiography. So the contents for today's topic is firstly we'll discuss about limitations of conventional radiography, then introduction to digital radiography, computed radiography, direct digital radiography, and lastly comparison of conventional CR and DR. So these are the topics for today's discussion. So, by the end of the session, you will be able to understand the setbacks of conventional radiography and how the digital radiography has advanced over the time period, and you will be able to learn how is image formation occurring in these types of radiography systems. So, let's discuss the first topic, limitations of conventional radiography. So, firstly, uh, in older periods, that is, we used to have conventional radiography system, that is, film screen system. So, in film screen system, how did we do the radiographs? We used the films and intensifying screen in its image formation process. Okay, so how is conventional radiography working? The film was placed between two intensifying screens, and these intensifying screen, when they were struck by X-rays, they will emit light. This light will expose the film, and then will process the film using chemicals. That is, we have a long step of processing. You might be remembering the processes like development, rinsing, fixing, and washing. So, this is how we process the film, and after the processing, we can manifest the image, and the film is ready for the radiologist to interpret. So, this is how conventional radiography was working. But we have multiple limitations to the conventional radiography. Okay, so let's see what are the limitations of a conventional radiography. First thing is radiographic film has a defined latitude, that is, the range of densities is very defined, that can be recorded simultaneously. So this problem is particularly highlighted in chest radiography, where 40% of lung area is obscured by heart, mediastinum, and diaphragm. So mediastinum and retrocardiac portion of the lung remain under the penetrated, and when exposure is given for optimal lung details. So this is a major limitation of conventional radiography. It only has a defined latitude, that is, it only has a range of few densities. Okay, so it becomes a problem in imaging structures like heart, because it contains organs of various densities, right? Now the second limitation is film screen systems are intolerant to exposure errors, with under or overexposure leading to loss of radiographic contrast. So there are exposure or errors occurring like underexposure or overexposure. So it will lead to the loss of radiographic contrast. Then films cannot be transmitted or duplicated without some loss of quality, and this involves significant cost. So in the modern system, that is in the digital system, it is very easy for transmission and duplicating, that is making copy of the image we have already captured. But in conventional film screen systems, the films cannot be transmitted or duplicated. Then there are limitations in acquisition, display, and storage of image. Then another limitation of radiographic film is the noise, which is inherent in these images. So noise is much higher in conventional radiographs. Then storage of conventional radiographs also poses a problem. Then nowadays we can store our data digitally, right? So the images we have acquired in the computer, we can store them for around 10 years. So storage is not at all a problem nowadays, but when we were using the film screen system, the storage of conventional radiographs always poses the problem. Then film quality can deteriorate with time, especially if chemical processing is suboptimal. Okay, so the X-ray film that we had while conventional times were uh, it can be deteriorated with time. That is, it gets destroyed as time passes. Okay, so these are all the limitations of conventional radiography. So this all led to the advancement in the field of radiography, and with the help of electronics and advancement in electronics and computer, we developed a digital radiography. Now let's see what is meant by digital radiography. So, before coming to digital radiography, comparing to the conventional radiography, we have much higher advantages in the field of digital radiography. So, let's compare what are the advantages of digital radiography. So, first thing is digital images do not deteriorate physically or degrade chemically over time. So, this is a better advantage, right? So, in the last slide we discussed about the limitations of conventional film. So in that one we discussed that the films will deteriorate by the passing of time, or it will degrade chemically. So that problem is rectified in digital radiography. Then the second advantage is they allow a true reproduction of quality from copy to copy and from generation to generation. So now we can have quality copies. So transmission and duplicating of the image data is also uh, better now. Then digital images are flexible, allowing a variety of manipulations such as magnification, cropping, edge enhancement, compression. So once the image is digitized, we have a variety of manipulations possible. That is, we can give the image magnification, we can crop the image, we can give enhancement, then compression. So these all are possible with digital radiography. Then storage was a main issue in conventional radiography. So coming to digital radiography, images are stored digitally and are available anytime with the implementation of PACS. Then a higher patient output through is possible as compared to FSR system. FSR means film screen system. So comparing to FSR system, we can the patient flow can be increased. How can we increase that? Uh, suppose we are doing a conventional radiography. It is a time consuming process, right? We will it will take much longer time to give the exposure. Then we'll have to process the film, develop the film, process the film, and all that things. It is a hectic way. So once we have a digital radiography, the workflow is much improved. We need only less time. time consumed is very less compared to the conventional system. So by that way, a higher patient throughput is possible as compared to FSR system. Then increased dose efficiency and wide dynamic range of digital detectors with possible reduction of radiation exposure to the patient. So digital radiography has its advantages also in the field of radiation exposure to the patient. So these are the advantages of digital radiography over conventional radiography. So now let's see what is digital radiography, what does digital radiography means, and how image formation everything takes place in digital radiography. So the basic definition of digital imaging is that any imaging acquisition process that produces an electronic image that can be viewed and manipulated on a computer. So that is the basic definition of a digital imaging. Okay, so what happens in digital radiography is a digital detector will replace the films and intensifying screens which was used in conventional radiography. Okay, so what happens here is in conventional radiography we used film and intensifying screens. In digital radiography we replace this film and digital screen. We replace this film and intensifying screen with the help of a digital detector. Okay. Now, there are two types of digital radiography system depending upon the type of detectors we use in the capture of radiographic information. So, digital radiography can be broadly divided into two types. There is computed radiography system and there is direct digital radiography system. So, before going to that, just let's just have a look at the evolution of digital radiography. So the digital radiography was first put into practice in the year 1977. So in how did we introduce digital radiography? It was introduced in digital subtraction angiography. Then here is a timeline showing the evolution of digital radiography. So by the end of 2007, we had portable CR systems. You can just go through this table. So this is the evolution of digital radiography. Now coming back, we were discussing about how we divided the digital radiography into two types: computed radiography, that is CR systems, and direct digital radiography, that is DR. So digital radiography can be broadly divided into computed radiography and direct radiography. So, computer radiography, it computer radiography systems use a storage phosphor image plate, that is a PSP plate, and direct radiography can be further divided into two types. So you shouldn't get confused here. Digital radiography can be divided into two types, that is computed radiography and direct digital radiography. Again, this direct digital radiography can be divided into two types. Depending on the type of conversion taking place, there is indirect conversion and there is direct conversion. Okay. So I'll give a basic definition for this. So indirect conversion means the detector will have a two-step process. That is, firstly, the X-ray will be converted into light energy, and then this light will be converted into digital image. But in direct conversion, there will be photoconductors such as amorphous selenium that will directly convert the X-ray photons into an electric charge. Okay, so there is no intermediate step there. It is a direct conversion. So um, yeah, that's about the division of digital radiography. Now let's look into each of these components separately. So firstly, we'll discuss about computed radiography. So, as I said, computed radiography, that is CR systems, they use a storage phosphor image plate. Okay. So these PSP plates are enclosed in a light, tight cassette. These PSP plates are coated with europium activated barium fluorohalide. Okay, so what are PSP plates activated with, coated with? They are coated with europium activated barium fluorohalide. So the CR system is also a two-step process. Okay, so there will be an image capture and an image readout done separately. So first step is image capture and second step is image readout. So here is a picture of a CR cassette. So this is how a CR cassette looks like, and here is a picture of CR reader into which we put the CR cassette and we'll do the readout process. So how does a CR works? CR system works. So in CR system, first thing is the PSP is exposed to X-ray. That is, in CR systems, the photostimulable phosphor plate is exposed to X-ray. We'll give the X-ray exposure, and what happens is the the storage phosphor, the X-ray energy is absorbed and temporarily stored by the crystals within the PSP plate. Okay, so the PSP plate contains photostimulable crystals. These are amorphous crystals. Uh, these crystals, they will absorb and store the X-ray energy. Okay, so PSP plate is exposed to X-ray, and the X-ray energy is stored by these crystals. And then the next step is to read the cassette. Okay, so readout process is the next one. So what happens in the readout process? In the readout process, the image plate, that is the PSP plate, after exposure to X-rays is taken to a CR reader, where it is scanned by a high energy laser beam of a specific wavelength. Okay, so what happens is a focused laser light is scanned over the plate. A focused laser light is scanned over the PSP plate. It causes the electrons to return to their original state and emit light in the process. Okay, so when the X-ray energy was absorbed and stored by the crystals, it what occurred was the electrons were jumped into a higher energy levels. Okay, so the electrons inside the crystals, they jumped into an higher energy level, while the X-ray energy was absorbed by these crystals. Okay, the crystals got some energy and the outer shell electrons jumped into a higher level. And what happens in the readout process is when we give the focused laser light over the PSP plate, the electrons which just before jumped into the higher energy level, they will jump back to the uh, original state. Okay, so these electrons which jumped into the higher energy levels, they will fall back to their, they will return to their original state, which results in the emission of light in the process. So this is what occurs during a readout process. What happens during a readout process? Focused laser light is scanned over the plate. It will cause the electrons to return to their original state and emitting light in the process. And this light is collected by photodiodes or photomultiplier tubes. Okay, so the light emitted by the crystal is collected by photodiodes or photomultiplier tubes, and then the signal is converted digitally into electrical signal by an analog to digital converter. So we'll have an ADC component. That ADC will convert the electrical signal, the digital signal into electrical signal. Okay, and after that, the electrical signal is amplified, digitized, and used to form an image. So this is how an image is formed in a CR. Okay, so the how is the process? I'll tell one more time. So firstly, we'll expose the PSP plate, that is this cassette, this PSP cassette. So we'll expose the PSP with the help of X-ray, and after the exposure is done, we'll take the uh, PSP cassette to readout process, right? So the X-ray energy is absorbed by the PSP crystals and stored within the crystals. So since the crystals got some energy, the outer shell electrons will jump into a higher level. And during the readout process, when they are scanned with the laser light, uh, the electrons which were jumped into the higher energy level will fall back to their original level, and that will emit a light, and that light is collected by photodiodes or photomultiplier tube, and then the the signal is converted digitally into electric signal with the help of an ADC. ADC means analog to digital converter, and thus the image is formed. And we can use the same cassette for further next studies. So how will we erase the image from this cassette? Using the with the help of exposure with white light, the uh, the imaging place is erased. Okay, so this is what occurs inside a CR system. So you can see here, this is the CR cassette, how it looks from outside. This is the CR reader. Then this is the image output we get, and here is some physics shown in the form of an image. So here is the patient, here is the PSP plate, and here is the X-ray tube. So what how is it working? We'll give the X-ray exposure to the patient and the cassette. So the PSP plate is now exposed. The exposed PSP plate, we are taking it to the reader, and inside the reader, we will scan the plate using a laser beam for around 45 to 60 seconds cycle time. And with the help of ADC, we'll digitally convert the signal into electric signal, and we'll get the image. We can post process the image with the help of the computer. Okay, we can do the processing and do the contrast enhancement. There are multiple post processing options available in a CR system. And once we get the image, we'll get the we'll do the erasure, and the imaging plate or the reader is ready for next study. Okay, now what are the advantages of CR? So comparing to the conventional film screen system, what are the advantages of a CR system? It is easy to use for bedside examination and immobile patient. Right. So we can do the bedside examinations with the help of an bedside CR machine. Okay, and for immobile patients too. Then the CR cassette can be placed in any position, thereby enabling flexibility for positioning for difficult views. So with the help of a CR cassette, we are able to position for difficult views also. Then multiple cassette sizes are available, and there is a better contrast resolution than the conventional system. Okay, and the main advantage of CR is the time. Okay, we can reduce the uh, consumed time, which is much higher in the conventional radiography system. So the time stipulated in conventional radiography system was very high. Here we can reduce the time due to the advancement in the CR system. So these are the advantages of CR system, but still the CR system has some drawbacks. Don't confuse this CR word with conventional radiography. Okay, CR stands for computed radiography specially. Conventional radiography is different, and CR is a is the division of digital radiography. So don't confuse that. What were we talking about? Drawbacks of CR. The drawbacks of CR is it is a time consuming technique. Now we are comparing CR with digital radiography, direct digital radiography. Okay, so comparing to that, CR is a bit time consuming technique, right? We have to first capture the uh, we have to first expose the PSP plate. It takes some time, and after that we have to put the PSP plate into the reader, and we have to wait for the readout process. And after the readout process is done, we'll have to do some post processing adjustments. So it is a time consuming technique. Then spatial resolution is lower than that of film screen radiography. So one drawback of CR comparing to film screen radiography is spatial resolution is much lower than that of film screen radiography. But contrast resolution is better in computed radiography than film screen radiography. So don't confuse both of them. So understand spatial resolution is lower than that of film screen radiography. Then thirdly, radiation dose required is same or more than film screen radiography. So radiation dose is almost same in both film screen and computer radiography. So computer radiography has an advanced in the aspects of radiation dose. So these are the drawbacks of CR. Now let's come to direct radiography, which is the most advanced form of digital radiography. So, direct digital radiography or just direct radiography is a way of converting X-rays into electrical charge by means of a combined image capture and readout process. So, DR systems can be further divided into direct and indirect conversion groups depending on the type of X-ray conversion used. Okay, so DR systems can be further divided into two types: direct conversion detectors and indirect conversion detectors. So, the first one, uh, direct conversion detectors, they have an X-ray photoconductor such as amorphous selenium that will directly convert X-ray photons into electric charge. Okay, so there is no intermediate step in between the uh, process. Okay, so this is how a DR detector will look like. Okay, so let's see how is direct conversion taking place. So what acts as a photoconductor here? We use amorphous selenium as a photoconductor. So let's see how direct conversion takes place. Here, what we use as a photoconductor is amorphous selenium. Okay, so direct conversion type of detectors uses amorphous selenium as photoconductor that converts X-ray photons into electrical charge by setting the electrons free. The photoconductor materials include amorphous selenium, lead iodide, thallium bromide, and gadolinium compounds. But the most commonly used element is selenium. Okay, so why are we using these elements? Because all these elements have a high intrinsic spatial resolution, and as a result, the pixel size, matrix, and spatial resolution of direct conversion detectors are not limited by the detector material itself, but only by the recording and readout devices used. So, what we use as photoconductor is amorphous selenium. So, it sends the electrical signal to a TFT. TFT means thin film transistor, and then to ADC. And the ADC signal goes to the computer for processing and viewing. So, the direct conversion is a simple mechanism. Okay. I'll just summarize once more. So, what happens in direct capture digital radiography? It converts the incident X-ray energy directly into electrical signal using a photoconductor as the X-ray absorber, and then send the electrical signal to a TFT and then to ADC, and the ADC signal will goes to the computer for post processing and viewing. Now let's see indirect conversion. Okay. So indirect conversion, it is a two-step process. Okay. So what happens here is first step is uh, the detector will absorb X-rays, and then secondly it will get converted into light. So a scintillator is the primary material for X-ray interaction. So when X-rays strike the scintillator, the X-ray energy is converted into visible light. Okay, so the first step is scintillator. The scintillator is the primary material for X-ray interaction. So when X-rays fall on the scintillator, it is converted into visible light. Then, this visible light is converted into electric charge with the help of photodetectors such as amorphous silicon photodiode arrays or CCDs. CCD means charge coupled devices. Okay, then it is converted into electrical signal, and similarly as the direct conversion, it is sent to the computer for processing and viewing. So what is the two important terms which comes in indirect conversion? One is a scintillator. Okay, and the second one is photodetectors like amorphous silicon or CCDs. Okay, so what happens in an indirect conversion? Firstly, the scintillator will absorb X-ray and convert into visible light. Then this light is collected by an array CCD, that is charge coupled device, or thin film transistor array. So, what is charge coupled devices? Charge coupled devices is a light sensitive sensor for recording images that consist of an integrated circuit containing an array of linked or coupled capacitors. Okay, so it consists an integrated circuit which contains an array or array of linked or coupled capacitors. So that's what a charge coupled device is. So X-ray is converted into light by a scintillator, such as thallium doped cesium iodide. Okay, so what is the scintillator we use in indirect conversion? It may we use a scintillator such as thallium doped cesium iodide. So cesium iodide is the scintillator material we use in indirect conversion. And what is the photoconductor we use in indirect conversion? We use amorphous silicon. So, what was the photoconductor we used in direct conversion? In direct conversion, we used amorphous selenium, right? Direct conversion, amorphous selenium. Indirect conversion, amorphous silicon. Okay. So, that's how an indirect conversion takes place. Now, let's see some main difference between digital direct conversion and indirect conversion. So, first differences, the basic steps, right? So in the direct conversion, there is direct conversion of x-rays to electrical signal, that is x-rays directly converted to electrical signals. But in indirect conversion, x-rays are first converted to light with the what is the component here, scintillator. Then the light is converted to electrical signal. What is the component here, photoconductor. Then uses a photoconductor that directly converts the absorbed X-rays into electrical signal without any intermediate light production. So the total light production process is not occurring in direct digital conversion. Okay, that is eliminated. The light production step is eliminated. So, in direct digital conversion, we use a photoconductor that directly converts absorbed X-rays into electrical signal. And what happens in indirect digital conversion? We will have a phosphor that converts X-rays into light, and then we will have a photodiode array that converts the emitted light into electrical signal. Then the detector material used in direct conversion is amorphous selenium. And what is the phosphor used commonly? That is, what is the material used inside the scintillator? Thallium doped cesium iodide or gadolinium oxysulfide. Then the signal does not spread as the applied high voltage separates the electrons and holes produced by absorbed X-rays. In direct to digital conversion, the digital does not spread, and in indirect conversion, the signal will spread. That is, the light scatter reduces the spatial resolution more with gadolinium oxysulfide or as phosphor than cesium iodide. Then the resolution of images is maintained as the thickness of photoconductor is increased. So if we increase the thickness of photoconductor, the resolution is affected. Resolution is maintained. Then in case of indirect digital conversion, with the increase in phosphor thickness, poorer resolution images are obtained. Okay, so as we increase the phosphor thickness, the resolution of the images are poorer. Okay, so in direct to digital conversion, the resolution of the image is maintained even if the thickness of the conductor is increased. So if we increase the thickness of the photoconductor, the resolution of the image is not altered. It is still maintained. It does not change. But with indirect to digital conversion, as we increase the phosphor thickness, the resolution will drop. Resolution is poorer. Then fill factor is almost 100 percentage in direct digital conversion. And in digital indirect conversion, the moderate fill factor depending on pixel size. So what is this fill factor? Fill factor is the area of detector that is sensitive to the X-rays in relation to the total detector area. Okay, so that's why we give the percentage. So it is the area of detector to the total area of detector. Okay, so area of the detector which is sensitive to X-ray in relation to the total area of the detector. So what does fill factor um, of this much percentage indicates? It means the given Suppose for indirect digital conversion, the fill factor is around 80 percentage. So what does that mean by this 80 percentage? It means that if the fill factor is 80 percentage, it means that 20 percentage of the pixel area is occupied by the detector electronics. Okay, with 80 percentage representing the sensitive area. Okay, so 80 percentage of the part of the detector is sensitive and 20 percentage is occupied by the pixels. Okay, so what is fill factor? Fill factor is the area of the detector that is sensitive to X-rays comparing to the total area of detector. Okay. Then last difference is moderate DQE for KV used for conventional radiography, but high DQE for mammography and KV range. DQE means detective quantum efficiency. And in case of indirect digital conversion, high DQE for KV range used in conventional radiography. So these are the general difference between direct digital conversion and indirect digital conversion. So this is a simple topic, some simple differences and image formation. So here is a picture of all three systems, that is conventional systems, that is screen film radiography, and then there is computed radiography system showing the physics of computed radiography, and finally there is digital radiography system in which it is clearly shown the indirect conversion and the direct conversion. Okay, so comparing all the three, the screen film radiography, the image processing in screen film radiography is done with chemicals, while the digital radiography side, that is computed radiography and direct and indirect digital radiography, they both doesn't require any chemicals. The processing occurs within a computer. Okay, so the processing occurs within a computer, whereas in screen film radiography the processing was done with chemicals. Okay. Then another difference is exposure latitude. Okay. So in conventional radiography, it is based on the characteristic response of the film, which is non-linear. Okay. So the dose response curve is non-linear. Whereas in digital radiography, so in digital projection imaging, it involves the using of a detector that can respond in a linear manner. Okay, so digital radiography is linear, and conventional radiography was non-linear. Then other important differences are imaging room. So for conventional radiography we had the old traditional x-ray room. Then for computed radiography also the same traditional x-ray room is required, but for digital radiography, that is indirect and direct digital radiography, we'll need a retrofit traditional x-ray room, or we'll have to install detectors in a new room. Okay, we can't use the same conventional radiography room for installing the digital radiography machines. Then another difference is use of cassette and film. So in screen film system, we had to use cassette and film and process them with chemicals. But in computer radiography, we'll use the cassette. There is still cassette, the PSP plates, and we'll process it in the PSP reader, And when it comes to indirect and direct digital radiography, there is no cassette and wheel process in the console. Yeah, so that's all the basic differences between all these three. And with the installation of a digital radiography system, we have another advancement in our radiography. That is the implementation of PACS. Okay, so PACS means PACS is a networked group of computers, servers, and archives that can be used to manage digital images. Okay, so it is a PACS is simply a network of computers. It's a group of computers which will provide the services for archiving the informations. Okay. Then PACS can accept any image that is in digital imaging and communications in medicine format. So we have a format in order to accept the image in a PACS. That is DICOM format. DICOM is the universally accepted format for accepting in a PACS system. So PACS will accept any image that is in DICOM format for which it is set up to receive, whether it is from cardiology, radiology, or pathology. So PACS is uh, the full form of PACS is Picture Archiving and Communication System. Okay, so from the word itself, it is clear that it is a system for archiving and communication. Okay, so we can securely store and we can communicate within the hospital or with different hospitals. So it is a platform for archiving and transmitting the informations. It can provide image access to multiple users at the same time, on demand images, electronic annotation images, and specialty image processing. The first full scale PACS in the United States was installed at the VA Medical Center in Baltimore in 1993. So PACS was first installed in 1993. Then it was made to interface to radiology information system, that is RIS. Then hospital information system, that is HIS, and electronic medical records, EMR. So we come across all these information systems, right? RIS, HIS, EMR. So this is all about PACS. All you have to know about PACS. So, with this, we'll conclude today's topic. So, I'll just give a brief summary. So, what our topic for the discussion was digital imaging, right? We started with what is conventional imaging. So, in order to understand digital imaging, we need to know the history of radiography, right? So, we started from conventional radiography. Then, we discussed about the limitations in conventional radiography, which required newer systems in order to replace the limitations. So we talked about the advantages of digital radiography, and then we came to digital radiography. So digital imaging is any imaging acquisition process that produces an electronic image that can be viewed and manipulated on a computer. Okay, so the digital imaging, the word itself shows that it is a digital format we can view with the help of a computer. So that is what digital imaging is. Then we discussed that the digital imaging can be divided into two types: computed radiography, that is CR systems, and direct digital radiography. So computed radiography systems had PSP plates, right? So the PSP systems are the digital acquisition modality that uses photostimulable phosphor plates to produce digital projection images. Okay. Uh, so with the help of PSP plates and PSP readers, we'll get the image. Then we talked about direct and indirect digital radiography, in which there was two types: direct conversion and indirect conversion. Okay, we use PSP plates in computer radiography, right? Like that, what we use in digital radiography is flat panel detectors. It is the common name of detectors in digital radiography. So, flat panel detectors can be divided into two types: indirect conversion and direct conversion. In direct conversion, the X ray was directly converted into electronic image, electronic charge, right, with the help of photoconductors. What was the photoconductor used in digital imaging? Amorphous selenium. Okay. Then in indirect conversion, indirect flat panel detectors, there was a two-step process. So in the first step, we had a scintillator. The scintillator will absorb the X-ray and convert it into light. And in the second step, we'll have photodiodes which will convert this light into electronic charge. So that was all about indirect conversion. And then we talked about PACS. So PACS is a networked group of computers, servers, and archives that can be used to manage digital images. And DICOM is the was the accepted format for digital images. DICOM is a standard that allows imaging modalities and PACS to communicate in the same language. Okay. So this is all about today's class. So the future of radiography is digital, and it is imperative that the radiologists and we radiographers should be familiar with the technical principles, criteria for image quality, and radiation exposure issues with the various digital radiography systems that are currently available, along with the technological advancements that are taking place. So these are the advancement in the field of digital radiography. So, with that, I'll conclude today's class. Thank you.